Hi everyone, welcome back. In this video, I wanted to continue our series on radar imaging. And the last thing we discussed was range migration algorithm or holographic reconstruction for synthetic aperture radar. I wanted to extend that to MIMO radar. So we've made one video on MIMO radar theory, and I showed you how you can use MIMO radar to get high resolution, and it's much faster and also requires fewer elements than, let's say, a phased array, but it's definitely faster than synthetic aperture radar. So for near field imaging, you could also use it for far field imaging, but um, you can it's very useful for high resolution near field imaging. So in this video, I thought I will show you how you can extend range migration or holographic reconstruction to MIMO arrays. It's very useful because MIMO is becoming very popular now. So this is based on a paper by Zuge and Yarovoy that I'll link in the description below, but we'll extend it a little bit more to, let's say, FMCW radars in this case, but it's almost the same as what they do in their paper. Okay, so let's get started. So this is, I think, number 9, which is MIMO range migration algorithm. So we saw that range migration is a very fast way to reconstruct images in the near field, especially that accounts for the spherical phase front. So you really don't make any approximations in terms of in terms of any planar phase front approximations or anything of that nature. So it's more accurate, you get better quality images, and it's very fast. Okay, so first I'll do a quick review of what we've done so far and what you need for this video. So we started with, FMCW range Doppler, and then we did pulse radars, and we also did step frequency radars for just a signal model. And then we showed that from these three, we can find a generalized signal model that we can use for image reconstruction, 3D imaging, and so on. And then we saw 3D SAR reconstruction, 3D SAR reconstruction using back projection, time domain correlation, and so on. We showed a bunch of algorithms are basically the same. And then we introduced the concept of MIMO radar and equivalent arrays and so on. And then we did finally range migration algorithm, or it's also known as omega K frequency wave number domain algorithm, or holographic reconstruction, and so on for SAR. So I highly recommend that you watch these videos. I don't want to start from scratch again, so I'll assume that you understand this one well, you understand this one well, and maybe to some extent this, and one of these three. So let's say FMCW. I'll focus on FMCW here because that's becoming more popular now for near field imaging. Okay. But you definitely have to watch these two videos and get a good understanding to be able to follow what I'm doing here. Okay, so now we will do RMA for MIMO radar. So in this video, I'll cover just the theory, and the next one, I'll show you a MATLAB implementation of how to implement this algorithm. I don't have any experimental data like I did for the SAR algorithm, but we can generate some synthetic data and see how to reconstruct from that. Okay, so we'll start as usual with the signal model, which we've seen many times, but just as a warm-up, we'll go through that. So let's say I have coordinate system, XY, and I have, say, my transmitter somewhere here, TX, some location given by this position vector RT vector. And let's say I have a receiver somewhere out here with a position vector RR. And say I have some target like that over some imaging domain R, capital R, let's say, or fancy R. And I have a point on this target that I want to focus on to. with my imaging algorithm. And let's just say, let's just call it a point on the target, not about focusing. Okay, some point on the target at location R. So that's my position vector. Then we know that this vector from basic geometry is R minus RT. And this vector is R minus RR. Okay. And then we said, okay, in case of MIMO, if you don't know what this is, you should go back and see the MIMO video. Said that SB, which is the IF signal in case of FMCW radars, or the post-match filtering result in case of pulse radars. In case of step frequency radars, is basically the signal that you measure. Okay, is a function of the distance R vector, transmitter vector, receiver vector, and K, which is the wave number, and is given by the reflectivity function f of R at this location times spherical phase front going from RTX to the target, given by R minus RT, another spherical phase front coming back from the target to the receiver, divided by 16 pi square mod R minus RT. So you can absorb the 16 pi square into this, it doesn't matter, but in this case, I've written it out explicitly. So if you don't know where this is coming from, I mean, this is essentially a product of two spherical waves whose Green's function is e to the minus jkr over 4 pi r, right? So it's a product of those two. Okay, if you don't know what that is, go back and watch the previous videos. All right. So we've already derived this before, and we said that this is for a single point at this location, but the measured signal SB tilde is an integral over all of these reflections from all points of the target. So that is triple integral of position vector belonging to the domain of integral of the target. And you can write SB here. RT, RR, K, DR. Okay. So this DR is nothing but dx dy dz. Right. And we also know that K is equal to KT, which is equal to omega C plus beta T over C for FMCW radars. It's a time domain signal. And K is equal to omega over C for pulsed and step frequency radars. And RT is not RT, sorry, modulus R minus RT is equal to square root of x minus xt square plus y minus yt square plus z square. I'm assuming zt is 0. So let's assume the transmitters and receivers are all on a single plane, 2D plane, where we assume that the coordinate system is on that, the origin of the coordinate system is also on that plane. So that's why the z value is 0. It doesn't have to be, you can make zt non-zero as well. Similarly, r minus rr is given by square root of x minus xr square plus y minus yr square plus z square. Okay. So that's essentially the signal model. And the idea of imaging is to see how we can reconstruct f from this measured SB tilde, right? That's what imaging is, or at least radar imaging is. Okay, so to do that, we will resort to this algorithm called range migration. It's much, much, much faster than back projection, as we saw for the SAR case. Okay, so let's get into it. All right. So let's start again by writing out the expression now in terms of Cartesian coordinates, xt, yt. It's a function of xr, yr. One mistake I made here is that this is no longer a function of r because we're integrating over r. So it's only a function of rt, rr, and k. And since zt and zr are both 0, we can write it only in terms of xt, yt, xr, yr, and kt. I'll use kt because I'm talking about FMCW radars here, but it doesn't matter. The signal model is the same. Okay. So we saw that this is triple integral xyz of f of xyz e to the minus j kt, let's say rt plus rr, divided by 16 pi square rt rr, right, where rt is modulus of r minus rt and rr is modulus of r minus r. Okay, and of course we have the dx dy dz here. Okay, so the first step is to take a 2D Fourier transform with respect to, similar to how we did in SAR range migration. Here also we will take a 2D Fourier transform with respect to xt, yt, and another 2D Fourier transform with respect to x, r, y, r. So that's essentially a 4D Fourier transform with respect to the variables xt, yt, xr, and yr. Of course, all these 4 variables are independent, so it should be fairly straightforward to take a Fourier transform. Okay, so let's do that. So when I take a Fourier transform on the left, this becomes SB tilde of kxt, which is the spatial frequency with respect to xt. We have kyt, kxr, kyr, and then kt. And that whole thing is equal to, there'll be a lot of integrals now, so let's see if we can keep track. Okay, so we have triple integral xyz, f of xyz, let's say divided by 16 pi square. None of this is a function of the xt's and yt's and so on, so they can be pulled out and we can take the Fourier transform in. So the first Fourier transform is xt yt e to the minus j kt square root of x minus xt square plus y minus yt square plus z square. It's not a very nice looking y. There you go. Okay. Divided by square root of same thing, x minus xt square plus y minus yt square plus z square times e to the minus j kxt xt minus j kyt yt dxt dyt. So that's the first 2D Fourier transform, and I've only taken this part. So I've only included this part and this part, and we are left with another 2D Fourier transform, which can be taken further inside because xt, yt are unrelated. So xr, yr, and xt, yt are unrelated. So the other Fourier transform comes in now. So times xr, yr e to the minus j kt. This subscript t has nothing to do with the transmitter. It's to represent time domain. X minus xr square plus y minus yr square plus z square over square root of x minus xr square plus y minus yr square plus z square e to the minus j kxr xr minus j ky r. My bad, actually. This should not have a subscript t. Oh no, that's right. Yeah. Ah, k yr yr. That's correct. And dxr dyr. Okay, it's a big equation, about I don't know, 1, 2, 3, 4, 5, 6, 7 integrals overall. And of course, all of this has the dx, dy, dz at the end. But it's not actually very complicated to solve this. It's fairly straightforward. So if you remember from the SAR video, we said that an integral of this type of, let me use a different color, of this is one integral, right? And they're all separate integrals, so you can deal with them separately. This one, both these integrals can be solved using the method of stationary phase, right? I'll make a separate video on this. I think it's useful to do that. Maybe I'll post it right after this. So if you don't know what method of stationary phase is or how to compute it, then I talked about it a little bit during the SAR range migration video, but I'll make a separate video. Okay, so we can actually solve these two integrals explicitly using stationary phase approximation. So the solution is the following. So this becomes triple integral x, y, z, f of x comma y comma z divided by 16 pi square. So the first integral becomes 2 pi j over kzt e to the minus j z kzt times e to the minus j kxtx minus j kyty. And the second integral is the same again, divided by kzr e to the minus j z kzr minus j k xrx xrx minus j k yry. Okay, so this can be simplified a little bit more. Let's say where actually, let me just write on what is kzt is square root of kt squared minus kxt squared minus kyt squared, and kzr is square root of kt squared minus kxr squared minus kyr squared. So now that we have those substitutions, maybe zoom in a little bit. Okay, nice. So one more substitution we'll make. So this is actually, it comes from the method of stationary phase itself. But what we can say now is we can define a new variable kx as kxt plus kxr and ky as kyt plus kyr, and we can say kz is kzt plus kzr. So when we do this, this simplifies a lot, right? So that integral becomes triple integral of x, y, z, f of x comma y comma z divided by 4 kzt kzr. There is actually a negative sign that comes from the product of these two j's. So I can put that in, or you can ignore it, doesn't matter, because eventually we'll take a magnitude when we do imaging. Okay, times e to the minus j kxx minus j kyy minus j azz dx dy dz. Okay, that's very nice because now this expression at the end looks exactly like a 3D Fourier transform of f of x comma y comma z divided by 4 kzt kzr. Right? So, okay. So this is equal to SB tilde of kx t ky t kxr kyr kt, right? Which means that f of x comma y comma z can be written as the 3D inverse Fourier transform of SB tilde of kxt kyt kxr kyr kt not divided by, sorry, times 4 kzt kzr. And this kzt kzr acts like a high pass filter on the image, right? So that can be expanded out further as the 3D Fourier transform, inverse Fourier transform of 4 kt k 4 kzt kzr times the 4D Fourier transform of our measured signal SB of xt, yt, xr, yr, and kt. So this is the final range migration reconstruction. So we start with our measured signal SB at these locations, xt, yt, xr, yr, and these time periods, the IF time domain signal, that is. The first step is to take off. So step 1 is a 4D Fourier transform. And then step 2 is this high pass filter plus 5D to 3D interpolation. And we actually implement it because this signal is a 5D signal, whereas here we're applying a 3D FFT. So we need to interpolate that 5D signal onto the 3D FFT. And that interpolation is done at this stage where we do, if you remember, we did set kx equal to kxt plus kxr, ky was kyt plus kyr, and kz was kzt plus kzr. So this interpolation actually is non-trivial. It's quite difficult, or not difficult, but a little bit tricky. You need to make sure you do it correctly. So if this is done correctly, then at the end we can take the last step. Step 3 is a 3D inverse Fourier transform. Okay, so that's pretty much it. This is the range migration algorithm for MIMO radar. It's fairly straightforward if you understood how to do range migration for SAR. So somewhat relatively shorter video, I suppose. So I'll make a follow-up video on implementing, or not implementing, but on method of stationary phase and how we actually solve this integral. I won't derive the result from of method of stationary phase, but I'll show you a couple of examples, the actual statement and a couple of examples of how to use it to solve integrals of this kind. Okay, with that, thank you so much. Look forward to a video on the MATLAB code implementing this algorithm. I will also upload these notes onto the website from which you can download them and use the notes if you like. There are also other notes from previous videos that I put up on there. You can find the link to the website in the description below. Okay, thank you. Have a nice day.